Thank you, Anmar. So I did ask Anmar what he wanted to hear, and he didn't respond. So I picked this topic. Um, and I started working on this because, you know, we were locked down in mid-March, and then I was at home, and then I started to like, you know, I was like on Twitter for, you know, I'm on Twitter. I go visit Twitter once every few weeks or so. And I was just seeing all these physicists were tweeting about their models. And then I thought to myself, wait a minute, you know, like why should some astrophysicist do a SARS model, you know, a CoV-2 model and not me? So I thought, you know, I should try modeling this too. And I also saw some like papers that I thought that the models were just making predictions that didn't make sense. So I really wanted to dig deeper into this and see what was going on. And then this is like, you know, kind of occupied me for the last 3 months. And so, you know, I've been taking this quite seriously. Did I just kill something? Okay, so probably like many of you, every day I stare at this screen, at the Hopkins screen, and on June 28th was an ignominious day because that's when we crossed 10 million infected in the world. Although we're still far from 7 billion or 6 billion, whatever herd immunity is. We're pretty high, and we have, you know, 500,000 deaths already, and it's over 100. It's near 130,000 dead in the U.S. already, and the U.S. is nearing 3 million. So just from June 28th to now, the U.S. has, you know, increased by about. It's been increasing by about 50,000 a day. So this thing is growing, and it's it doesn't just grow purely exponentially either. It kind of grows, it plateaus, and it grows, and regions go down, regions go up. So, you know, we'd like to really know how is this really progressing and what's going on, right? So no doubt all of you now know what the reproduction number is. That's what epidemiologists talk about, and I'll talk about this more in depth. But we want to know, you know, how fast is this spreading? And that's, you know, basically if one person's infected, how many on average do they infect? And if that number is greater than 1, then this thing will grow. And if it's less than 1, this thing will shrink. We want to know how deadly is this thing, right? So we want to know what is the actual infection rate. And, but in order to do that, we really need to know how many are actually infected. So the number that are reported as cases are not the number that are infected, obviously, right? Because some people get it and they don't have symptoms. We all know about these asymptomatic cases. So and then they recover probably, and they may not even know it themselves. Other people get sick, not sick enough. I know in New York, people told me that unless you were really, you know, really dying and ready to go to the hospital in the early stage of the pandemic, if you were just sick, they would not have any capacity to test. So if we really want to know what this reproduction number is, we want to know what the infection fatality rate is. We need to know how many people are actually infected. And we need to know this in the absence of wide-scale testing. Because even though now, I mean, the first tests that they had were PCR tests. So these are tests to actually test for the presence of virus. And these tests have very, very good specificity. So if you have it and it says you're positive, it's almost 100% you are positive, but they're not very sensitive. So if it says you're negative, there's still a 30% chance you have it, right? So they're not perfect. And then there's serology tests, which test for antibody, which just tests to see whether you've ever been infected. And so these things have the opposite problem. They're very sensitive, but they also have lots of false positives. Although NIH has the best test going right now, the antibody test, we have one out there. So hopefully we will have a pretty good serology test. But it's gonna take a long time before we can just test for antibodies to know how prevalent was this thing. So the question then is, given what we have, which is the number of observed reported cases, the number of case recoveries, and the number of case deaths, can you infer the number that are infected? Okay, so that's the inverse problem we're trying to solve. And so in order to do so, we need some sort of model. And then, you know, the standard model is this SIR model. And this model basically says that if your people are divided into two categories, or more than two, but let's start with two. Initially, there's an infected population and a susceptible. And an infected person interacts with a susceptible. There's a probability, there's a chance that the susceptible becomes infected. And then that infected person then can either recover, which is the SIR model, but they can also die, which is usually never placed explicitly in an SIR model. I don't know why. But historically, people don't deal with SIRD models. They always call them SIR models. But I mean, there's a disappearance rate. So R doesn't have to mean recovered, it's just removed. So what the R is removed, not recovered. In this case, I will call R recovered, and then I will separate the removed into recovered and dead. So what this is, it's a network-dependent birth-death stochastic process, right? So first of all, you have to calculate the probability that you will actually run into an infected person if you're a stochastic person, and if you're a susceptible. And you also, there's only a probability that you will be infected if you do run into an infected person if you're susceptible, for various reasons, right? They may not breathe in your face. That you may have some innate defense. You might have some, you know, this is something that Yoram Vodovitz and I are talking about, was like maybe how to model like any innate immunity you have for either T cells or previous exposures. There may be various reasons for what this is. So to model this thing, we really don't know how to model it. But the most simple model we have is the mass action SIR model, or mean field SIR model, which assumes that everyone's in a well-mixed population, right? So this is the model that all of you know, I'm sure. And so that the infected, there's just a probability that if S multiplied by I, and there's a rate beta, and you normalize by N, which is the population. So the infected goes up, the susceptibles go down, and then the infected get removed with a rate sigma. So in initial condition, what we can say is that, well, if we say that initially the entire population is susceptible, or you can say N-1, and then one person is infected, but usually N is much bigger than 1, so you can just ignore the one person at N-1, just make an N, and so you can just substitute that in, and then you can just simulate this model, or you can do some analysis. It's simple enough that you can do a lot of analysis. You can get very far analyzing this model, which people have been doing for, you know, nearly 100 years. So, so if you start with I low, and if beta is greater than sigma, then and S is N, then you have, you know, beta I minus sigma I is a positive number. So this thing will then grow exponentially until it reaches a peak, and then it will come down, right? So that's the dynamics. And at the very peak, you can get a fraction, right? So, and that's 1 over R naught. So that is exactly the reproduction number. So, and that is also called the herd immunity threshold, because when the fraction of susceptibles drops to 1 over R naught, or generally people take 1 and subtract this number. When the number of infected, the fraction that are infected reaches 1 minus 1 over R naught, then the probability of meeting someone that's infected times the rate of being infected is less than 1, right? So even though the biology hasn't changed, just that your chance of running into an infected person goes down. So if the mass action model holds, then a pandemic should rise exponentially initially, then start to saturate, hit a peak when the susceptibles reach 1 over R naught, and then decay. That's not what we're seeing. That's the prediction. And initially, when people were, the first models that they used to predict, how many people would die back in January and February, they were using basically SIR models. And so, and that's why they were getting those giant numbers, right? So if it's 7 billion people on the earth, then and then the estimates from Wuhan was R naught was like 3, then 67% of the world had to get it before it would go down. Okay, that's in the absence of doing any mitigation. So we're, so dynamically I and S describe everything, but we want to know how many are removed, how many are recovered, and how many died. So those are just ODEs because we have a conserved quantity, which is the population. So we assume that the epidemic is progressing fast enough that births and deaths are not affecting it. Now, if this thing starts to drag on to years and decades, then you'd have to include the fact that people are moving around, they're being born, and they're dying from other causes other than COVID-19. So then the infection fatality rate would just be the total dead divided by the total infected at time t, okay? So if you take t to infinity, that would be the asymptotic value. Okay, so this is a non-decreasing number because d is always increasing, and then n minus s is also always increasing. So they're both always increasing, and then you get, so sorry, d is always increasing, n minus s is always increasing. IFRT does not have to be a non-decreasing. That can go up and down depending on how fast things are going. So we have this classic SIR model, which susceptible goes to infected, and then they are removed either, but that's not what that's not the data we have. We have recovered, we have observed, but really what we have is that we have susceptibles become infected, and then with some rate or probability, they can become a case. And then the case can then recover and observe. So what we have is we have C, R, and D are observables, and then S and I and U are latent variables, right? So latent in machine learning is just an unobserved hidden variable. So what we really want to do is we want to estimate I given C, R, and D. That's the game you want to play. So we have this SICR model, which I call the sticker model. Intentionally called it the sticker model instead of the CIRC model, which would roll off the tongue a little better. So now you have the susceptibles decreasing with based on whether you meet an I or whether you meet a C. So you have a Q times C. Q is the deflation or inflation factor of how cases are infectious, right? So if you happen to be somewhere where quarantine is especially effective, so once you detect a case, they are completely quarantined, then Q could be 0. But you could have a situation where cases are they're in the hospital, they're infecting healthcare professionals, or they could just be more infectious because they have a higher viral load. So Q may not be less than 0. And in some cases where cases are completely ignored, you just say, yeah, you have it, and you're sent home, then Q may actually be greater than 1. So we don't know what Q is. That's a parameter we need to estimate. And we don't know any of these parameters. We have some priors on what they are probably, but we don't know what they are. So we have to estimate beta, Q, sigma C, sigma U, sigma R, sigma D. We need to estimate all these things. Now, one of the reasons that it's been so hard to model is that beta is not time independent and sigma is not time independent because human behavior and policy changes, and possibly even because of biology, okay? So there could be the virus is mutating, the infectiousness is changing, but also just like whenever we're in lockdown, like right now, Maryland is still in a partial lockdown, and I know parts of Canada are in lockdown. Once you're in lockdown, then the probability of meeting an infected person goes down. And so you can model that by just simply saying the infectious rate changes. Even though the mechanism for why beta changes could be different, you can always model as some time-dependent function. And similarly, testing capacity could change, or the definition of cases. Like if you look at the Wuhan data, on one day, the number of cases increased by a factor of 4 or 5. And that was because they changed the definition of what it meant to have COVID-19. Prior to that was a PCR test. After that was simply that if you had a CT scan of your lung and you showed these like little glass, they call it like glassy little lesions in your lung, then that was called a case. So you can model a time dependence, and this is just some possible function you can model with more parameters. You could always make it more sophisticated. You can always add more parameters, and you could then try to fit those too. So those parameters, you have some idea of when the lockdown was put in place, but you don't really know how effective it was. So we're gonna, you can fit those parameters, and the talk will be about how do you fit those parameters. With the sicker model, the reproduction number you can also calculate. So you can calculate many ways. You can do it by using this generation method that actually calculates what's the average number, or you can do the cheap way, which is just simply say, well, there's a peak when I is 0, when the derivative of I is 0 and the derivative of C is 0, and then you can solve that and you get R naught, and you get the exact same number. So the cheap way gets you the number. And so now R naught depends on beta and sigma like before, but all depends on sigma C, sigma U, sigma is sigma R plus sigma D, and then Q. So that's just a more complicated formula, but still we can calculate it. So if we estimate all those parameters, you can now get the reproduction number. You can make the model more complicated, right? So obviously this model assumes that there's some constant rate of recovery, which is probably not true, because we know some people are, they recover in say 10 days, they might clear the virus. And some people may be in the hospital for 6 weeks. And we now know that there are these long haulers where, they got sick in February or March and they're still sick. So 100 days later, they still have symptoms. They're oscillating up and down. So that's something that Jorm Bodevoets and I and Judy Day, our collaborator, are trying to understand that. But so you can try to account for this biological discrepancy by adding more compartments, right? But as you add more compartments, you add more parameters. And they're all unknown. We don't know what these parameters are. So, so there's not one sicker model. There's lots of sicker models, and we don't know which model actually applies. And so the strategy I'll tell you is that what we do is we just fit every model. Okay, so we're leveraging Moore's law, and we're just going to use a lot of computer time. But there's another problem, which is, first of all, that SIR model that I showed you, the sicker model, is a mean field mass action model that assumes a well-mixed medium, which we clearly know is not the case, because right now in the United States, New York is going down. It has it well under control. Arizona and Texas are exploding. The next hot spots could be, who knows, Maine, Kentucky, Kansas. California went down, now it's going back up. It's very heterogeneous, and it's heterogeneous probably because of the network effects that people don't interact uniformly. You don't have the same probability of interacting with everyone in the country, right? You have your little cluster, and that cluster is in a cluster, and then these clusters are connected. So there's some network which we don't, fully understand. We don't understand. So we don't know what N is. Like if we are to model this thing, we don't, we don't know what the population is. Even if we're like saying, oh, this is the model for Italy. Well, it's like mostly in Lombardy, and do we include the population of Sicily, which is not affected yet? So N is actually not a fixed number. You can't just use the population of the region directly. You have to understand kind of the clusters, how it's interacted. So what we do is we just say N is a parameter and you fit the parameter. Okay, so you fit the population size. And also initially, one way you can make this, reduce the number of parameters, is you can say, well, initially as this is growing approximately exponentially, then you can just assume that the susceptibles are N. And you could just assume that it's a constant, and then you get a linear approximation, right? So that's just another model. Obviously, this will break down once the pandemic progresses. But initially, in the beginning parts, the first few weeks, it may not actually be too bad. So there's still more unknowns because we don't know what the initial condition is, right? We know that if you start at 0, then this ODE system will stay at 0. So you have to seed it with something. But remember, it's a latent variable thing. So how do we seed it? So the way we do it is that we say, well, we take the observable, which is the case. And then we just take we call day 0 the day that, the number of cases crosses the threshold. So 1, 10. 10 is actually a good number, but I'm going to show you data where we actually simulate from 1 because it actually gives some interesting results that I want to talk about. So let's just say the day of the first case, then you can say, well, assuming that all the parameters were fixed, let's go backwards in time and say, what would I be given the set of parameters given C? So then you can say, okay, I can infer I given the parameters. There's some relationship between I and C, using whatever approximation. This is a linearized approximation. You can get that. So now we have a fully defined ordinary differential equation system, but it's deterministic. Okay, so it's a deterministic system. And the whole point is that you're dealing with a noisy situation. So that my talk will mostly be about that. So what are the measures we want? So we want to estimate the case ascertainment ratio, which is the total number of cases divided by the total infected, right? And it's also a function of T because the case ascertainment ratio is not fixed in time. It will change as testing capability changes, right? Or maybe the virus mutates and it becomes more virulent, then you get more cases just by virtue of the fact there's fewer asymptomatic, or the other way around. So it can change in time. And also the IFR, which is the infection fatality rate, also ratio also can change in time. And so total case deaths over total infected up to time T can go up and go down. And then we have the time-dependent reproduction number. So remember, R0 is the bare reproduction number, which assumes that S is N, and it assumes that beta and Q, all the parameters are fixed in time, whereas now they're time-dependent. So you can get this time-dependent reproduction number that also accounts for the fact that you're non-linearly reducing the number of susceptibles, so that's accounting for herd. So even in the absence of doing anything at all, RT will decrease just by virtue of the fact that the number of susceptibles is decreasing, right? So the probability of running into an infected person starts to go down. So we want to fit this model to data. And the observables are the rate of new cases. So every day you get new cases. Every day you get new recovered, although not all regions report that. And then every day you get new deaths. Okay. So, and these are positive numbers, right? Or they're non-negative numbers. So you can have 0. You can have 0 deaths on a given day, and then you can have 1 or 10 or 100, but you can't have negative. So you have a system where we have sigma CI, sigma RC, and sigma DC, and we want to infer all the parameters and C and I. Okay, so the first question is like, supposing you had perfect information, is this even are these parameters identifiable? Like, is this system is this question even well posed, right? Because you could just end up having a situation where it's not. And you can imagine we have, 3 data points, although it's in time, so it's 3 time-dependent data points. So in principle, an infinite number of points, so an infinite amount of information. And you want to infer all the parameters. So in this case, you have, and then beta, and then also you want to infer IFT, the actual fraction of the number that is inhibited at a function of time. That's the epidemic curve. You want to infer that, and you want to infer that CFT. If you do the math, you get 7 conditions for 8 unknowns, which means that this is not identifiable, right? So even in perfect information, you can never fully specify all the parameters, right? So there's ways, the way around it is you just simply fix one of the parameters. And then you just estimate the others. Or there is one thing, one saving grace for this is that if you know when mitigation was applied, then beta will change, but it adds one more parameter, but now you have two regimes, and that becomes an identifiable system. So, so this thing is quasi-identifiable. It's not really identifiable, but we have some good priors on some of the parameters. We kind of know how fast you recover. We kind of know how infective you are, so we can narrow down some of these parameters. And so it gave me hope when I did this analysis before I started fitting it. It gave me hope that it was possible to get some meaningful parameters. And then especially some of the measures we wanted, that even though you have this 7 conditions for 8 unknowns, which means that one parameter is going to be correlated with another one, that the two kind of divide each other out in some of the formulas, so that it didn't really matter if you didn't pin them down, because we were looking only at these ratios of things. So I'm actually going to spend a lot of time talking about Bayesian inference. And this was a battle that was fought, I would say, from about 60 years ago to 20 years ago. There was a raging battle in statistics over how to do statistics. And about 10 to 20 years ago, the Bayesians completely won. It is, so in every statistics department in the country, I don't know if any statisticians are listening, or if you can just go down to your statistics department. Okay, I can't speak for all statisticians, but for the majority, the statisticians have all acknowledged that Bayesian inference has won the battle, that statistics should be all Bayesian, although that doesn't discount the old, kind of frequentist things. So for example, for those that don't know any statistics or refuse to learn statistics, of which I was in that camp before I got to NIH, the p-value, you've all heard about p-value or confidence intervals. These are concepts from what's called frequentist statistics. And then if you hear this term, the credible interval or the posterior probability, these are concepts from Bayesian inference. And so now if you read papers, those things are used interchangeably. Just because the Bayesians have won doesn't mean that the p-value has lost all value. It actually has a meaning, a specific meaning within Bayesian inference and the confidence interval and all these things. So you can keep your old statistics, but the Bayesians have won. But I realized that this had not actually percolated down to everybody, because I was just in this meeting where a bunch of modelers were getting together and we were discussing how to model the uncertainty in the models. And I was surprised that a large fraction were still not Bayesians, okay? They were still not using Bayesian inference. So I'm just letting you know now that I'm gonna take a strong political stance on this and say that there is only one way to fit models, and that is Bayesian inference. And you can use whatever method you want, but what you're doing is you're doing some version of Bayesian inference. So what is Bayesian inference? There's many books written on this. There's textbooks written on this. There's like evangelical speeches on this on YouTube. There's, people have been fighting. Like I said, this was a raging battle in statistics for 50 years, possibly. The way I think about it, it's simply just doing statistics by just applying the rules of probability. That's it, okay? So all you have to do is just, if you want to analyze any system, all you do is you apply the rules of probability. And really, you only need 2 rules, right? Because we all know the first rule is that the sum of all the probabilities equals 1. That one's internalized, everyone knows that one. So all you really need to know is that if you have a joint probability, it can be decomposed into a product of a conditional probability and another probability. And it can be decomposed in lots of different ways, okay? So there's no unique decomposition of a joint probability. That's the first thing you need to know. And then the second thing you need to know is that if you want to get a probability of something, you can just marginalize over the other variables, okay? So these are just trivial laws of probability theory that every undergraduate in the world knows. And that's all you need to do when you're doing statistics, okay? So you don't have to know, do I need to apply the Fisher exact test? Do I need to apply the chi-squared test? Do I want to do the rank, whatever? You just say, I'm just going to apply the rules of probability. It really makes statistics simpler, like way simpler, at the expense of computation. So I will discuss that. So we want to fit a model to data, right? And so data has noise, right? It always has noise, especially biological data, right? There's always some noise in it. And so then the question is, you have some model and it depends on parameters, and yet you change the parameters, then you get another, another estimate. So which one do you pick? What parameters do you use? So the standard way of thinking about that is you have some model, it depends on parameters. So you have some prediction Y, and you have parameters theta. And then you just simply say that the probability that the data, you just calculate what's the probability the data came from this model, and then that's called the likelihood, okay? So a conditional probability is a probability when you talk about D as the variable conditioned on Y. It is a likelihood when you talk about what is theta given D. And the reason it's a likelihood is that when you integrate this conditional over D, you get 1. So that's normalized. So that's why P of D given Y is a probability. But if you look at theta given D, that is not normalized. You integrate over theta, you do not get 1. In order to get 1, you need to multiply this thing by P of theta, and then you can integrate over theta. So a likelihood is not a probability, but it gives you information about the fit, because the maximal likelihood, which is what people do, and in fact, that's what generally, if you are to do a least squares fit, then what you have done is you have maximized the likelihood that the data came from a normal distribution or a Gaussian, okay? So if you assume that you have some model, that the model's the mean, and then you assume that the data is going to be generated from this model with some normally distributed noise around it, then the log of the likelihood is this mean squared, the squared error. And then if you just sum over all the squared error for all the points, you get mean squared error. So whenever you're doing a least squares fit, you are maximizing likelihood for a presumed normal distribution. Now the noise may not be normally distributed, in which case then you're just, you're not actually doing it. You're going to miss out on something if you don't have the actual noise model. So having the noise model, getting the likelihood right, is part of the game of fitting these models. So you can't just blindly go and do least squares. Although it will mostly work, it will give you a pretty good fit, but that's one thing, right? So if you're just do maximum likelihood, you just say, oh, here's the parameters. Then you want to know, well, how confident am I in these are good parameters? Because if you imagine that sigma is really, really big, the noise is really, really big, then a lot of models kind of fit about the same. So even though this thing is a maximum, a neighboring set of parameters fits just epsilon worse, right? So then you want to have some sort of sense of how confident are you in these parameters. You want to have a sense of what is the probability that the parameters are good. So that's why you need statistics and you need Bayesian inference, okay? And in fact, in frequentist statistics, they have a hard time dealing with how good is a model, because they have things, the chi-square test. They'll look at all these different tests. They have all these little but because philosophically frequentist statistics, the only thing that can have probability distributions are random variables. Okay, so random variables by definition are quantities that are generated by some probability distribution. Whereas the Bayesians just say any quantity can have a probability distribution, right? So the raging battle, the philosophical battle was, well, how can the number of people in my house be a random variable, right? It's always the same, right? So if I was to look at the house, it's kind of like the Schrodinger cat kind of quantum mechanics debate. It's the same kind of thing. It's like, if I look in a house and I want to know what's the probability of how many people in the house, are the number of people in the house the random variable, or my observation? What's the random variable? Well, the Bayesians don't worry about it. They just say you can assign some probability. It's just some real number between 0 and 1. You can call it a belief if you want, or you can just say, if I were to just statistically examine houses and count the number of houses and take the number of people and divide by the number of houses, then I get an estimate. and I can get the distribution. So what we want is, we want to say, well, these are things we'd like to know. We'd like to know what is the probability of the parameter given the data, right? So this is what Bayesian inference is all about, because you just simply use the fact that the joint probability can be decomposed in two ways. So the conditional probability of theta given D is just equal to the likelihood, which is probability of D given theta times P theta over PD. Now, you've probably seen this formula a million times, and some of you get it right away and you just go to town, and some of you else are probably just glazed over and just don't get what the point of this. This thing seems like a silly identity. How do I get any information out of this at all, right? And so I think I was like that for a long time. I just sat there and said, whatever. It had made no impact on me. I just said, yeah, whatever. But it actually has meanings, because what it says is that a likelihood function, all this equation says is that you can turn a likelihood function into a probability if you normalize it. That's all that Bayesian inference is just take whatever thing you have and normalize it. And once you normalize it, it becomes a probability. And once you internalize this small little concept, okay, which to me took me months to years to actually get, it totally changes everything about what you think about everything. For me, anyway, changed how I think about everything. Because I realized that to make something a probability, which is something they teach you on the first day of, whatever, statistics class, you just normalize it. But it never actually stuck in my head what that meant until, much, much later. So to get the parameter posterior, I just simply normalize the likelihood. Now it becomes a posterior. To get projections of future data, I want to know, well, what are my projections? Well, what is the probability of new data? D tilde is new data, given old data. Then I just simply apply the rules of probability. Well, I know that P of D tilde given theta, that's the likelihood. Then I just integrate it over the parameter posterior, and then and that's it. I just apply the rules of probability, and that's all I did. Now, these integrals is the main reason why Bayesian inference didn't take off until about 20 years ago, is that to calculate these integrals, if you have a lot of parameters, like say you have 15 parameters and you need to do an integral on 15-dimensional space, those people who do numerical analysis knows that that's extremely hard to do. It's very, very hard to do. So Bayesian inference is about how do you calculate these integrals. That's what it is. And, if you read a Bayesian textbook, most of it will be about, what are the different methods to compute these intervals. So what we have now is we have this model, which is a latent variable model, and we have the data, which is, I changed notation here for some reason, sorry. That should be sigma C, sigma R, sigma D. And now we need a noise model. Okay, so we need to know what's a noise model. So if you're to think about a birth-death process, a stochastic birth-death process, and if the events are assumed completely randomly and uniformly, then the counts are Poisson. That is, in fact, the definition of a Poisson distribution. The Poisson distribution is the count distribution of a completely random uniform process. So if I were to assume that you just sat there and the probability of being infected is totally constant in time and unvarying, then you would expect a Poisson distribution in a number of counts. But in reality is different, right? Because first of all, people are heterogeneous, so your probability of being infected is going to differ. Probability of infectiousness differs. There are these super spreaders, or going to a bar and yelling loudly 2 feet away from each other is a good way to get virus. If you start to engage in different behaviors. So if you include all this heterogeneity and the fact that there's misreporting, cases are misclassified, some countries might be performing outright fraud and not reporting correctly. The number of tests you do will change, and so forth. So we can try to account for that by saying, if you just take a Poisson model and you are to just increase the variance of a Poisson model, in statistics, probability theory is called over dispersion, then that would be a negative binomial distribution, is a Poisson distribution with extra variance. And the variance parameters is phi parameter, and it just kind of adds some fraction of the standard deviation you know, the mean. Remember that in a Poisson, the beauty of the Poisson distribution is that the variance is the mean. It's a single parameter distribution. So you don't need to know what, add anything else. And now you make it a 2-parameter distribution by saying it's the mean plus, and the variance is now the mean plus a little bit of extra. So you can then, the whole idea is you want to compute the posteriors and the projections, and you want to do these integrals. And the way you do these integrals, there are many ways to do these integrals, but one way that is now taken hold is the Markov chain Monte Carlo, which is a way to do the integral by sampling only where the function is tall, right? Or basically sampling in proportion to the height of the integrand. You could say it that way. It's the Markov chain Monte Carlo. So you don't have to actually integrate this thing over everything. Now remember, the reason that we need to do a simulation at all is because although I'm doing this integral, I don't have an explicit formula for the integrand, right? It's the outcome of some process. So I can't just, like, you know, go to, you know, whatever, Mathematica and just type in a function and say, what's the integral, right? I don't know what the function is. So I have to numerically integrate it, which would either, some people would just divide this thing up into a grid, but if you think about 10 parameters and you just make the grid, you know, 10 in every direction, it's 10 to the 10. It starts to become big, right? 100 parameters, 10 to the 100. Then it becomes a really big grid. So you got to sum over all these things. So Markov chain Monte Carlo is a way to shortcut that. And in fact, there's different versions of Markov chain Monte Carlo. There's something that's called Hamiltonian Monte Carlo, which kind of searches space more efficiently. And now there's what Stan, which is a tool that does this for you. It uses a technique called no U-turns Monte Carlo, or nuts Monte Carlo. So, but, you know, and then there's variational methods to try to do this quicker. There's all sorts of ways. But essentially what you have is you have the SIR model, which is a deterministic model. And you're saying that, oh, this model is generating predictions for the mean rates of emission for cases, recovered cases, and dead cases. And that mean rate is being decorated by noise from a negative binomial distribution. Okay, so that's what we're fitting. And we're trying to infer the parameters and the measures. And so another thing about the big fight between the Bayesians and the frequentists was that people always argued about priors, saying that, oh, you're biasing your fit because you have to put priors in. The Bayesian would respond, even in your frequentist land, you have priors that you don't even think about, like the fact that there's just only one variable that you need to fit as a prior, the fact that, you know, like that calculus works as a prior. So, you know, there are all sorts of priors that you use. In this case, you definitely need to have priors, because otherwise you're searching infinite space and it's going to take forever to search infinite space. So one thing about the Markov chain Monte Carlo, there's a theorem that says it will converge eventually. There is no theorem that says how long it's going to converge. There probably will never be a theorem because it depends on the system at hand. And so in order to give yourself a head start, because you know, all you know is that if you run this thing forever, it will eventually converge to the correct distribution. But you know, if you want to do it in a finite number of times, then you have to do empirics. And so you have priors. And so we have some priors. And then you also want to reparameterize things so you get a better condition model. So these are examples of priors I've used in simulations. And changing the prior changes the model. So a different prior set is equivalent to saying I'm fitting a different model, right? So this is just my expectation of where things are. So, you know, some of these things I took from the fact that they have estimates already on what some of these parameters are. Other ones are just guessed. Like the population, I just said, oh, you know, it's a log normal distribution, which is a very, very fat tail distribution. So it doesn't really confine you. It's just a positive fat tail distribution. And say it's like, you know, whatever. If I'm looking at some population like New York, I can say, well, it's, you know, 1 million people or something with some distribution. And then what we're trying to predict is the case ascertainment ratio, total cases divided by total infected, IFRT, and RT. So there's lots of models. So which model do you use? Okay, so there's various strategies for doing this model comparison thing. One is that you're trying to balance fit with complexity, right? So obviously, if you add enough parameters, you can always get a model to go through every point, right? And that's, you know, that's called overfitting because it has no predictive value because, you know, so the way the Bayesian way to get around balancing fit with complexity just says, let's compute the probability of the model given the data. And that's just, you just use Bayes' rule, which is the probability of the model given the data is the probability of the data given the model times the probability model divided by the probability data. I also have to say that people have been like bent out of shape over what does P of D mean, right? What is the probability of data? That makes no sense. It's just simply the probability of the data given summing over all the models or all your parameters. Okay, so there's nothing mystical about that thing. It's just, that's just an integral. But anyway, so you can just say, okay, so then what you're saying is like, I'm going to take the model that maximizes P of D given M if I assume all the models have the same prior, then, you know, that's called the Bayes factor. Okay, but then, and that's something that I used to do, but then I realized, you know, what you really want to know is how well is the model making a future prediction? So what you really want to know is like, how well did the model predict data given the model, right? So you want to maximize prediction. And so that's called cross-validation. And then there are all these information measures, AIC, AKIK, information criterion, then there's W, widely applicable information criterion. These are all various approximations to this thing. And you can just do leave one out cross-validation or leave future out cross-validation. So you can do all sorts of different things. But essentially these methods are just ways you want to maximize prediction. And then so then you can just you can either take the best model that can predict, or you can do what's called Bayesian model averaging, which is to say, well, now I have a probability of how well the model performs, either by P of D given M or P of D tilde given M. I can use that as a weight and just average over all the models. Okay, then I can weight it by its performance. So that's called Bayesian model averaging. So we're you know, we do both. We do maximize and we do Bayesian, and we get a roughly same thing. And then we look at various models. Okay, so I simulate lots of different models. And you know, these are the attributes of the models. Some are linear, some are nonlinear, some include mitigation, some don't. Some have the Q factor is 0, some it's not 0, it's a fitted parameter, the case time dependence, 2 compartments. I fit, you know, multiple models. The most recent run I've done, I fit 12 models on the entire world, which is like 250 regions. So it's 12 models on 250 regions. And then, you know, and then, so each run takes a few hours between, for some regions it's 1 hour, you know, or less than an hour to 24 hours. Some regions take forever to converge, they take 3 days. And so it's thousands and thousands of hours of computer time. So here's Canada. So here's some examples of how the model performs. So, you know, and then those are the uncertainty bands. Those are in Bayesian statistics, it's called a credible interval. So that's just the uncertainty in your prediction based on integrating over all the parameter uncertainty and the noise uncertainty that you think your data has. So here's Canada. So you've done a pretty good job squashing down RT, that after about 50 days or so, you have the virus pretty well under control. You're getting about 20% of your cases. So you have about, you know, 80% are unaccounted for, and you have a death rate between 1 and 2%. And probably most of that was because, remember in the initial stages, I do remember reading about it, that unfortunately COVID-19 got into nursing homes. So most of your deaths are just due to nursing homes. So the actual non-nursing home infection fatality rate is much lower than 1%. So, you know, one of the lessons we've learned is that A, don't ever check into a nursing home. B, don't let virus get into a nursing home. So Italy, you know, as you recall, Italy was one of the first hard hit. They really slammed down RT. And even in Italy, even though they have very widespread testing, they're still, the case ascertainment ratio is still asymptoting around 20%. And they're just a lot more elderly in Italy, and people are susceptible. So the death rate, the actual death rate accounting for unaccounted for is pretty high. It's still, over 2%. Georgia, as you recall, was one of the states that opened up early. And so these are simulations up to May 31st, I think. So they opened up at the end of April. So this is 1 month of opening up. So you can see that the cases didn't really increase. And this was like giving people confidence that, oh, you can just open up and nothing can happen. But there's a delay. There's a long time. And if you see that they didn't really get RT very much under control under 1, and now Georgia's going up. New York, on the other hand, took it, they kept the clamps on, so they got RT very low. And so New York seems to have things under control. And the death rate in New York is about 1%. They were a little bit better at keeping it out of nursing homes. United Kingdom was like probably the one in Europe that was the least responsive initially. So it took them a long time before they got it under control compared to like Spain, which got it under control much earlier. And they have an extremely high death rate. I don't know what's going on in the UK, but they have a very high death rate. And Spain too has a pretty high death rate. Singapore, the Asian countries are very strange because like South Korea, while they got it under control, they're not really suppressed it to nothing. And yet nobody dies in Singapore, like there's almost no deaths. So I don't know what's going on in Singapore. People are not dying. We have no idea what this is. Is this genetic? Is this environmental? Whatever it is. But Asian countries have lower death rates, except for China, which has a very high death rate. So non-China Asian countries seem to have a lower death rate. The ones competing with the US to see who can have the most cases, Brazil and Russia, we see that Russia definitely did not have it under control. Russia has an anomalously low death rate. I don't know if that's due to false reporting or not, but they actually break our models. We have a hard time fitting Russia. They are very different from the other regions. Brazil, on the other hand, has just kind of given up. They've controlled it, but I think Brazil is just gonna try to go for herd immunity. And so we'll probably see Brazil being one of the first countries to hit herd immunity, and we'll just see how much damage it actually does. So we fit all the countries. Here's another sampling of them. You can see that the case ascertainment ratio, the more astute observer will say, what's going on? Spain has a case ascertainment ratio greater than 1. What is that all about? How can you have cases be more than the number of infected? Well, this is because our model assumes community transmission. So when you have a case ascertainment ratio greater than 1, what that means is that your infection initially is being sustained only by immigration, by people coming in, and it's actually dying out. So Spain, if they had done contact tracing right away, could have just squashed it right away, because by week 2, you can see that case ascertainment ratio has gone below 1. And then by week 3, it's like pretty low, which means that it's starting to take off. The number of infected are taking off. So by May 17th, most of the world has it under control. They're all below 1. So if we were to persist right now, then this is on May 17th. And obviously, if you stop locking down, you can go above 1, and parts of the United States are above 1. The reason I didn't fit it beyond that, because I don't have the relax from lockdown in my model yet. So that's the next thing I need to add. So if you look globally, this is Australia. This is what the model is saying. Australia, India is really good at finding cases. I don't know, the model could be wrong. But it changes over time. You get better over time generally. Infections, I know I'm out of time now, so I'll just kind of go through. We have a preprint of this, and we're going to upload a new version of it, and probably write a paper at some point, maybe. I don't know. I've been telling my collaborators that the old publishing model is kind of over. We have this on medRxiv, maybe that's just good enough. Do I have to actually publish this paper? I don't know. So the infection fatality rate, I think this thing is probably killing at a rate of about 1%. And that's highly age dependent. Like it's very high for elderly and ones with predisposed preconditions, and low, probably low for healthy young individuals. And so, you know, we see that this thing is changing over time. The death rate in China is very high, maybe because of lots of smoking. I don't know. And the reproduction number, here you can see some countries have it under control and other places do not. So in the United States, Brazil, there are just a lot of states that are not below 1. So they're opening up and they do not have it under control. And you know, this thing can be very slow, because if your reproduction rate is exactly 1, then you're going to be growing, you know, you're growing non-exponentially, right? You're just adding the same number of cases every day. So if you're very near 1, you're going to grow very slowly. And you may not notice that you're having cases until like 1 or 2 months later. So that's one of the problems of being near 1, is that this thing becomes very slow. And so, you know, again, you can make little maps and you can see that R0 is decreased everywhere. Africa has been spared so far, but Africa might be the next hotspot. That it might be coming there next. So finally, like, why are the models so bad? Like, why have they been really terrible, right? In fact, people don't really believe what they say anymore. People, you know, you say, oh, there's another modeling study, but you know, I know one model was, you know, they had to refit every 3 days. They had to refit because their like prediction was so bad. So they basically could not predict beyond 2 days. And so one is, you know, data quality. There's misreporting. There's changing standards. There's maybe outright fraud. There's the one that I think is the most important is that there's network effects that we're just not accounting for. It's the fact that this thing is not happening uniformly everywhere at once. It's like kind of like, it's like sparks in a forest fire. You get a spark. It may burn, it may go out on its own. It flames low, you know, it could be wet and then it flames faster. And so it's happening all over all at once. So you kind of have to fit each region independently. There's physiology effects. It's clearly not a Poisson process. There's probably multiple compartments. We don't have that right. There's lots of differences between people. A major part is behavioral modification, that even when you don't lock down a place, people automatically change their behavior. And when you like release from lockdown, people change their behavior in non-predictable ways. I know that in Baltimore, there's, you know, where I live, the people are very vigilant about social distancing, but other parts of Baltimore, they're not. So depending on where you are and how things are. And people are flying around the country. That's why I think like Maryland, right now, we kind of have it under control, but we're not super well under 1. And my prediction is that Maryland's going to spike back up in August, September, right before school starts. So we can cancel school again and make our lives all miserable for the next 6 months. Maryland's probably going to come back up. And then there's, you know, there's this discreteness, low number effects. I'm using this mean field model, although people do have stochastic models, and it's not like their discrete stochastic models are so much better. So we have a preprint of this work if you want to read about it on medRxiv. All the code is publicly available on GitHub. GitHub is definitely the way to go. And then since this is recorded, I may not put the slides. I just may put a link up. But you know, I generally, all my talks, I have slides on my blog. And I also, you know, blog on my blog if you want to read about my musings on stuff. So thank you very much. I know I went over. I apologize. Anyone have questions, please ask. I can stay as long as you want, but you know, feel free to leave. I won't be offended.
Thank you very much, Carson, for a very, very interesting talk. For one thing, I'd like just to say that you were preaching to the choir, because the crowd here in CAMBAM have been pushing hard for them to use Bayesian Inference to do any model fitting. And I think I convinced a large number of people there in this group to use it as well.
Yeah. I was a little afraid.
In fact, I was teaching it even in one course. So
okay, so that was a little. You're probably all like falling asleep during that or surfing.
No. That's
okay.
Not what I'm saying. I'm just saying. I mean, there are people who are not part of CAMBAM that are apparently attending. So it's glad that you're emphasizing the same philosophy that I have as well.
Okay, great.
So I'll keep my questions until the end, but I'll let the people attending to ask their questions. There are a few comments that have been written, so feel free to read it. Be brave enough to read these comments as well on your own.
Yeah, I have to like I
these two
still
thoughts?
haven't figured out how to use Zoom yet, so I still have to like figure out how to get back the old window thing. Oh well,
So,
whatever.
no,
I
no.
can't read the comments because I can't figure out Zoom. But oh wait, is this how you do it? Oh yeah, here we go. Chat.
So let's see the
Carson,
questions.
while you're reading those, I have a question. So obviously that was a
Sure.
great talk. So now there's some, I think it's still preprint, suggestions that the viral strains in Europe are different from the ones in Asia.
Yeah,
There's additional mutations
yeah,
supposedly can infect 10 times better, although interestingly, they're again suggesting that the actual disease severity is not worse. It's not clear. But the bottom line is that now you have this kind of a heterogeneity, which, I mean, you pointed to some of these issues, but, you know, in trying to say, well, why is Asia keeping its death rate relatively low versus, you know, Europe, and apparently in the US, a good chunk of the virus that came into here really came through Europe.
yeah, yeah. In fact,
So
yeah.
So there's
Yeah, there's a
obviously
great,
some misrepresentation going on.
that's
So, yeah.
really good point. Yeah, that's a great, in fact, that's what I want to do next. So, so there's a great website called NextStrain, which tracks the viral genetic code in real time. So you should definitely go to nextstrain.org, I think is what it's called, COVID, and you can just watch it. And so they have the whole map of the virus. You can actually map how the virus progressed, and, you know, went from Asia. It went from China to Italy to parts of Asia, and then Italy, it went through Europe, and then it got to New York through Europe. And then there was a mutated strain at some point. And Ian, you have to go. Sorry, my son. Ian.
Can you come?
So it seems like you almost need to simulate separate diseases.
Yeah, so what I want to
You know what I
include
mean?
is include the next strain data to see the pandemic in real time, fit the entire world at once.
Dad,
Sorry, I have to deal with my like itinerant son. Ian, you have to go. I'm in the middle
what
of a
does
talk.
itinerant mean?
Go, yeah, go.
What does itinerant mean?
Sorry.
Wow, Carson. So it turns out you do have children. Okay, great.
Yeah.
This whole time, Carson's been saying he can't do certain things because of kids, but now we all know that it's real.
I do have kids, and in fact, I'm a tragically old dad. I have a kid, and I'm like, near retirement, and I have a young kid. So that's the tragedy of my life. But anyway, so yeah, that's something I want to do, is to actually see, use the next strain data and then fit the model based on using, constraining regions based on the strain to see whether or not there's a true effect. So that's definitely something I'm interested in doing. It just requires a lot of computer time and a lot of coding. So, but I'm trying to recruit this kid to do some coding for me. So.
Any other question?
Yes. Hey, Carson, this is Karen from Texas. Thanks for your
Hey,
talk.
Karen.
I'm really glad I got to hear this. My question, and I just got off the COVID ICU, if that's relevant. My question is, are you seeing a correlation with like places with the higher caseload and mortality? Because I can definitely see, like, as we start to run out of equipment and personnel get stretched thin and we're tired and burned out, like we just can't provide the same level of care. Like, are you seeing, like, do you think it's because maybe Singapore doesn't have a huge caseload, they have universal health care, they have a small number of patients, so they can really
Yeah, that's a
like
good
take care of
question.
them?
In fact, I haven't mined the results to check for that correlation. So if you want to do it, go ahead, please. Yeah, that's a great question. I don't know. I don't know. Seems very plausible. We we have all the results. They're all dumped. So anyone who wants to analyze the results are free to do it. So that's something that we should do. So Karen, yeah, definitely ping me offline. We can do that.
Yeah, but I was just going to say, I've been talking with my cousins in Singapore, and even the migrants, the migrant dorms that you've heard about those big outbreaks, all of those folks are being prophylactically tested, and they all have access. All of them have access to Singapore's universal healthcare system.
Right.
And my guess is they're not completely overburdened. So I can tell you, even if hospitals say they have beds, like we're pretty stretched thin already here.
Yeah.
And when you start running out of like your key personnel, your key equipment, like ventilators, high flow nasal cannulas, like respiratory therapists and pulmonologists, like the level of care is going to drop when you stop having experts take care of these so-called ICU beds. So I'm guessing like there's probably a pretty big piece of like basically lower standards of care because of the burden on hospitals.
Yeah, I think you're right. And that could be why Italy had such a high death rate initially. It's probably because they were first hit, so they weren't ready for it. The other countries maybe later that they were a little bit ready, and also that the techniques got a little better, right? So you know what to test for, like oxygenation level in the blood is a clear indicator. Loss of sense of smell is something that people now know, so that, you know, go smell a rose every day. If you don't smell that rose, go get tested, okay? Because definitely there's a lot of ACE2 receptors in the olfactory system in humans. So the virus definitely can start to like knock out your olfaction. So, but yes, thank you for that.
Thanks, Carson.
Any other comments, questions?
Yes, I actually wanted to go back to that question of the false negative rate. That's really something that we grapple with a lot because we've been like repeatedly testing our patients who ultimately end up being positive. I don't know, that's actually just more of a comment, but it's a real issue because we're consuming a lot of tests, a lot of test swabs,
Yeah.
a lot of protective equipment to do those repeat tests, but I don't really have a better answer because we don't want them to go escape.
Yeah, what we need is we need an antigen test, not a PCR test. We need an antigen test, right? So, which people are working on. So once we have an antigen test, then we can at least test much more frequently and cheaper. Because right now you still need to get the sample, and then, you know, you have to run it through an RT-PCR machine, which takes time and money. So, but once, you know, your arm can weigh in. Once we have an antigen test, if we ever get one, then that will make things. Yeah, the false negative for PCR is a big problem because it's really high, and you can see why it's pretty high, right? You're sticking this Q-tip up a nose. I mean, you may miss virus, right? I mean, it's not guaranteed you're going to get the virus, and then you have to make sure that the sample is not contaminated and makes it in there, and then we have the primers that are only on for certain parts of the virus, and, you know, you might have a mutated form and the primer doesn't bind as well, and then you get like lower detection rates, or who knows. There's lots of ways things can go wrong. So yeah, we're just shooting in the dark. I mean, I have to say that anyone who makes some confident pronouncement on what's going to happen is just basically saying it on priors and not on any like model. I just don't like these models that claim, oh, we can predict how many people, if everyone wore a mask, how many fewer people. I just don't see how they can do it, because I just don't see what data did they use to figure out the assessment of a mask. So I'm not, you know, let me first say that I wear a mask everywhere I go. I firmly believe that a mask will work just based on physics, but I don't know what the reduction parameter is to put it in my model. All I do know is that if I reduce infectivity, things will go down, right? But I don't really quantitatively know. So I'm highly skeptical of everyone's model, including my own. I mean, I don't believe my model really, you know.
Can I ask just two questions? So one of them, when I look at your sicker model, one thing I've noticed is that the infected, and then you go to recovered, but the recovered actually never go back to infected. Even
Yeah.
Strong evidence that there are in patients that get reinfected again.
Yeah.
Reported in Japan and South Korea, I think. This
yeah,
is one
I know.
question.
That is a
The
true
question
weakness.
that I have is, you know, they talk about the wave and the second wave and third wave, which I understand it based on my limited understanding of this disease, is that you have a half bifurcation, and that, or not close by, but at least you have these damned oscillations. So there's some sort of oscillativity that generates these waves. So do you, I mean, I didn't see.
Well, I think based on like what we know about coronaviruses in general, and say the flu, is that any immunity, that if you're infected, you probably have immunity for say 3 to 6 months, let's say, right? And we're still in the initial phases of the epidemic, so we're nowhere near herd immunity really anywhere except maybe the Bronx, which might be at 50%. But, you know, outside of like the Bronx and parts of Italy, or you know, we're not near herd. So I would say that effect is probably going to be smaller than just infecting susceptible. So I don't think the oscillations have come yet. They could be coming. I mean, we could get oscillations. The seasonal thing may actually be something like that, right? That it just so happens that we know that from flu vaccines that within 6 to 8 months that the efficacy of the vaccine itself, your antibody count goes way down. So just to a vaccine, we know that. And so you can be reinfected by the exact same strain of flu like a year later. You know, it's just like so it's not just that the flu is mutating or the cold virus is mutating, but you could be reinfected by the exact same cold virus a year later. So that is absolutely true, and it's not in the model. But it would just be another parameter to fit, right? So just
So Carson actually alluded to the modeling work we've been doing of the sort of immunology or immune response to the virus. And we can get simulations and parameter sets that result in recurrence without the need to hypothesize a second infection. Basically, the virus can be knocked down, but not fully. It will appear that you have recovered, but in fact, it's still there, and then it'll pop up again. And that'll happen on a shorter time scale than what Carson was talking about. So, and I think, you know, we made the case that given just exactly what everybody was just talking about now, the limits of detection of the assays, you could have the second bounce up be just near that limit of detection, and then you would have a big debate as to whether that's a false positive or not. And that's in fact what happened in the Korean case. So, so we, right now, based on the modeling that we've been doing, and it's modeling, we hope to have data as well from both clinical and possibly animal sources. Then we currently think that you don't need a second infection. In fact, if you were immune, let's say, and the data seems to suggest that somewhere between 3 to 6 months of immunity, barring a vaccine, then that would not be able to, you know, that would go against the idea that you're going to get a second peak of virus detectable within a month or less of the original infection. So, and it clearly is different. We simulated based on specific parameter sets that are, you know, presumably individual genetic variations, variations in the essentially the degree of infectivity of the original virus, et cetera.
Yeah. Any other comments? Yeah, we do not have this under control. Definitely do not.
Any other question?
Yeah, Carson, here's one for you. I know Governor Abbott here in Texas finally put on a masking order. Is that going to be enough to save us? Or how good do masks have to be to save us here?
If you get R naught below 1, you'll start to decrease. I mean, it's pretty simple. On the other hand, you could just go for herd immunity. You could accelerate it and just have like COVID parties, and then you could just try to accelerate it, and that'll get it over quicker too. I mean, you're in the middle of a train track and the train is coming, right? And you have two options. You can run towards the train or you can run away from the train. And so, you know, pick your poison. That's all I thought. I don't know, you know.
How about just getting off the track and going to the right or to the left? I mean, that would seem to be even better.
Well, you're on a bridge, you know, the metaphor is you're on a bridge, you're walking across the bridge and you're a third of the way and the train's coming, right? Do you run toward you? It's closer towards the train, but further away from the train. So then you have to calculate how fast you can run versus how fast the train is going. And that's exactly where we are at this point. Like in the US, we've totally lost control. So, you know, you get R naught below 1. I mean, that's it. Everyone just stay at home. If everyone just put on a hazmat suit and stayed at home, this thing would be over in 3 weeks probably, right? So, I mean, that's it. That's the problem is like, you need a coordinated action to get this thing to work. You'd have to have everybody just go in their little pod for 3 weeks and play video games for 3 weeks, get IV drip for their food, everyone in their pod. And 3 weeks later, you know, the ones that are really sick, we could find and you can just, you know, treat them. But the other ones, everyone will be cleared.
Any questions? Okay, so on that note, let's thank Carson. I think you should publish that work. Don't just leave it in GitHub. Really publish it.
Yeah, we're trying to. It's really hard to get it.
I've seen in other places, other talks, so other research done by other people. So,
all right, thank you. Thank you, everyone.
Thank you very much. This is really very enlightening, and see you around.